Welcome back. In this video, we are going to learn to identify the nature of the state of stress of the material or metal stock undergoing deformation in a rolling process by first identifying the type of the forces involved at the interface between the roller and metal stock using fundamental principles such as Newton's third law, second, and then using those forces involved at the interface, we will draw free body diagrams of one of the rollers and metal stock at their interface for visual clarity and better understanding of the state of stress of a point on the surface of the metal stock. Since we are going to use this question as a learning reference, which is from GATE 2013 MESET A, let's first read out this question and try to analyze and understand it for what is given and what is asked. In a rolling process, the state of stress of the material undergoing deformation is. Alright, so what this question is asking is about the state of stress of the material that undergoes deformation in a rolling process. Alright, so before drawing a general setup or diagram of a rolling process, let's begin by understanding the basic operational workings of a rolling process. Alright, a rolling process is a metal forming operation in which the thickness of a metal stock in a form of a strip or sheet is reduced while keeping its width generally constant. This reduction in the thickness is achieved by passing metal stock between two opposingly rotating rollers or cylinders of equal diameters that are pressed against the metal stock with equal forces, maintaining a small gap which becomes the final thickness of the metal stock between the rollers. This results in different incoming and outgoing speeds of the metal stock due to the fact that the volume of the metal stock remains unchanged by assuming it to be incompressible or of constant density. Alright, now let's draw a general setup of a rolling process. Alright, so we have a general setup of a rolling process. This is the side view of the rolling process with breadth of the metal stock and the rollers go into the screen. Alright, here in this diagram, the metal stock goes between the rollers with a velocity v1 and comes out with a velocity of v2. Alright, and the thickness of the metal stock before deformation is T1 and after deformation is T2. Alright, and the rollers rotate in opposite direction with upper roller rotates in the counterclockwise direction and the lower roller rotates in the clockwise direction, pulling in the metal stock. Alright, now as we can see in this diagram that the rollers press the metal stock with equal forces F. Alright, so the rollers press the metal stock with equal forces F. Alright, this pressing action due to these forces generates interface pressure Pn, which is also a normal force per unit area at the interfaces between the rollers and metal stock. So, the pressing action of the metal stock by the rollers with equal forces F generates interface pressure Pn at each interface between the metal stock and the rollers. Alright, and this pressure Pn that can vary acts perpendicularly on both contacting surfaces at each interface between the roller and metal stock. Alright, so the pressure Pn acts perpendicularly on both contacting surfaces at each interface. Alright, between the metal stock and the rollers. Alright, and this pressure Pn can vary along the interface. Alright, meaning the pressure Pn acts perpendicularly on both the upper roller and metal stock along their contacting area at this interface. Alright. Similarly, the pressure Pn acts perpendicularly on the lower roller and the metal stock along their contacting area at this interface. Alright. Because from Newton's third law of action reaction, equal and opposite normal forces act perpendicularly on both contacting surfaces at their interface when they are pressed against each other. Alright, here this pressure Pn represents a normal force per unit area at each interface between the metal stock and the rollers. Alright, so this pressure Pn acts perpendicularly on both contacting surfaces at each interface in opposite direction. Alright, because of Newton's third law of action reaction. Alright, let's consider a side view of the interface between the upper roller and metal stock and draw pressure distributions with an intensity of Pn, which is actually a compressive stress at contacting surfaces of both the upper roller and metal stock separately. Alright, so after separating the metal stock and the upper roller slightly, we have drawn pressure distributions on the contacting surfaces of both the metal stock and the upper roller. Alright, here interface pressure Pn acts perpendicularly on both of these contacting surfaces. Alright, in other words, interface pressure Pn acts perpendicularly on each point of the contacting surfaces of both the metal stock and the upper roller. Alright, since the rollers rotate such that so as to pull the metal stock in between them, reducing its thickness and causing metal stock to move from left to right. This pulling action is the result of the friction force that arises on the contacting surfaces of each interface between roller and metal stock. At the beginning of the rolling operation, the metal stock has a near zero velocity while the rollers rotate in the directions as shown in this figure. So when the metal stock comes in contact with the rollers, there exists a relative velocity or a slip between the metal stock and the rollers. Alright, and this generates a friction at each interface between the metal stock and the rollers. Alright, to prevent this relative motion or to make the relative velocity between the metal stock and the rollers at their interface zero. Alright, or reduce this relative velocity. Alright, and this friction force that acts on the metal stock at each interface starts to pull the metal stock in between the rollers. Alright, keep increasing the velocity of the metal stock and trying to match it with the velocity of the roller at the interface. Alright, and the direction of this friction force on any roller is such as to prevent its rotation, while the direction of this friction force on the metal stock is such as to pull it in between the rollers. That is, the friction force try to prevent relative motion, which is why it arises in the first place between the roller and the metal stock at each of their interface. Alright, therefore, to prevent the relative motion at each interface between the metal stock and the rollers, the friction force on the upper roller must act in this direction. Alright, in the direction opposite to that of its rotation. Alright, and on the other hand, the direction of the friction force on the metal stock at this interface should act in this direction. Alright, so that the metal stock gets pulled in between the rollers. Alright, now let's move to the next page. As the side view of the contacting area at each interface between the roller and metal stock is a circular arc. The friction force is distributed with an intensity of Pf that can vary along each interface, which is also a friction force per unit area on the contacting surfaces of both the roller and metal stock in opposite direction at each interface. Also, following Newton's third law of action reaction, meaning The contacting surface area of the upper roller exerts friction force on the contacting surface area of the metal stalk along their interface. On the other hand, the contacting surface area of the metal stalk exerts friction force on the contacting surface area of the upper roller along the interface but in the opposite direction. Alright, similar to the case of the interface pressure, where the contacting surface area of the upper roller exerts interface pressure Pf over the contacting surface area of the metal stalk over the interface, whereas the metal stalk's contacting surface area exerts the same interface pressure Pf on the contacting surface area of the upper roller over their entire interface. Alright, now let's draw the distributions of the intensity of the friction force, which acts as a shear force because shear force acts on a surface parallel to it that has an intensity of Pf, which becomes a corresponding shear stress on the contacting surfaces of both the upper roller and metal stalk separately in the already considered side view of the upper interface. Right, so we have drawn the distributions of the intensity of the friction force Pf on both the metal stalk contacting surface and upper rollers contacting surface. Alright, and here we can see that the intensity of the friction force on the contacting surface of the upper roller acts in this direction. Alright, whereas the direction of the intensity of the friction force on the contacting area or surface of the metal stalk is in this direction. Alright, and both the intensity of the friction force and the interface pressure are always perpendicular to each other at any point on the surface of the metal stalk at contacting areas. Alright, now if we consider any point on the plane surface of the metal stalk that is at the interface of the contacting surfaces of both the roller and metal stalk, we would see that that point is subjected to a compressive stress Pn and shear stress Pf simultaneously. Alright. In other words, the material of the metal stock is subjected to shear stress and compressive stress together at the contacting area at each interface. Alright, and this simultaneous action of the shear stress and compressive stress causes the material of the metal stock to deform at each interface, thus reducing the thickness of the metal stock. Alright, so let's go back to the first page and try to answer this question. In a rolling process, the state of stress of the material undergoing deformation is compression and shear. Alright, so the correct option is C.